All right, so here's number 12. We have an asteroid in a highly elliptical orbit um, that carries it between 0.17 and 2.47 astronomical units from the sun. So, I mean, that would be like extremely elliptical, um, and that's much more like a comet. But at any rate, what's the semi-major axis? First of all, so that's good. That'll be our part A. And then, how often does it cross the Earth's orbit in days? And we're going to round both of these numbers to two places past the decimal. And right below here, I've got the both answers. So part A, it's going to be 1.32 AU, and part B is going to be it crosses the Earth's orbit every um, 276.96 days. All right, so how do we come up with these numbers? First of all, if it carries, so here let's draw a quick picture. I'll do that over here. Um, so let's say that this is the Earth's orbit. Okay, so there's the sun in the middle. So what's going on is this thing would this would take it um, what is it, an asteroid, right? It's actually much closer to what a comet would look like. So it's going out twice that distance and then coming in, um, much closer than the Earth. In fact, it comes in closer than the orbit of Mercury for that matter. So now, how do we do this? If this is the closest point and this is the furthest point, and they gave us those two numbers right there, you basically take the average of the two. All right, so this is the answer to A. All right, so the average of these two. All right, so this is going to be, I'll call it A sub average. All right, so the average is going to be 0.17 astronomical units plus 2.47 astronomical units. And then since you're just adding up two of them, divide by two, and that's what the semi-major axis is. In fact, that's the idea of what the semi-major axis is. It's the average distance um, that an object is from the sun or from its star. In this case, we're talking about our sun. All right. So anyhow, so here let's do the calculation. We just have to put these numbers in here. There it is. All right. So 0.17 plus 2.47 equals, all right, and then divide that by two. So the answer to part A is 1.32. All right, so that's what we get. So on average, it's 1.32 astronomical units from the sun, right? On average, right? Because it's varying between these two positions, 0.17 and 2.47. All right. So with that in mind, so how do we get the answer to part B? Well, we just have to figure out what the period is. All right. And so Kepler's third law tells us what the period is going to be. All right. So um, the period squared is going to equal the semi-major axis cubed, and the semi-major axis, remember, is the average value. All right, so it's going to be 1.32 cubed. All right, so this is a different problem. All right, and then of course to get what p is going to be the square root of that. All right, so it's the square root of 1.32 cubed. All right, so we got to cube that, and that number's already in my calculator, so it makes life a lot easier. All right, and remember the period will be in years. All right, so I'm going to raise that to the third power. So there's the 1.32 raised to the third power um, equals, all right, so that, and then if I take the square root of that, so that's the period. The period is roughly 1.52 years. All right, so this particular asteroid orbits the sun once every 1.52 years. But let's change that into days, right? But, well, it tells us that in this problem. So I know that in 1 year there are 365.26 days. All right, so that's just the definition of a year, which of course is how long it takes the Earth to go around the sun. But so we're going to calculate the period of this thing in years. Well, sorry, we did it in years. So we're calculating the period in days. So I just multiply this number, which is already in my calculator, times 365.24. All right, so there it is. That's the period of this asteroid is 500 and 552, sorry, 553.9, 553.91 days. All right. Now, if you think about that, right? Um, just look at this picture that I have. Um, in this, like as the asteroid is going around the sun, right? It crosses it in one of its periods. It crosses the Earth's orbit once, and then it crosses the Earth's orbit uh, a second time. So in one of these one of the time it takes, the time in days that it takes this asteroid to go around the sun is that, this many days, 553.91 days. So we know that during that period it crosses the Earth's orbit twice. So I'm going to divide that number by 2, right? And so every 276.9, well, it's 955, right? But I'm going to round it to 2 places past the decimal, so it's going to be 276.96. So the answer to this is, this is the answer to part B. Every 276.96 days. So that happens right here, and that happens right here. So every 276.96 days, it crosses the Earth's orbit. All right, so that is problem number 12. All right, so, oh, you know what? I didn't mean it to say escape velocity. All right, so here, let me redo this problem a little bit. I didn't realize it said escape velocity, and I'm just reading it now. It says calculate the density in grams per cubic centimeter, and it says and the escape velocity, which we've already done. We did that like 2 problems ago. Vesta, which is the third largest minor planet in the asteroid belt, 30 years ago, you would have said that was the third largest asteroid, but the 3 largest ones have been reclassified. They're large enough to now be considered minor planets. At any rate, Vesta, which no matter what you call it, it's still out there. So let's we know the radius of Vesta, we know the mass of Vesta. Let's calculate the density. All right, so that's all we're going to do. We're not doing this escape velocity part because we've already done that. I just realized that. All right, so this one, the density, of course, is the mass divided by the volume. Excuse me, divided by the volume. All right, so that's supposed to be an equal sign. So the mass of this is in kilograms. So kilo is times 10 to the third. So if I just rewrite this, it becomes 2.59 times 10. So since it's 10 to the 20th times 10 to the third, it would be 10 to the 23rd grams. All right, so that's pretty easy. The volume one is the one that's a little bit more involved. So they give us the radius of this thing as 262. I just did this problem very similar, where we calculated the surface gravity and the escape velocity. At any rate, 0.5. So it's in kilograms. Sorry, kilometers. That's the radius. And to convert that directly, 1 kilometer is 10 to the 5th. That's supposed to be a 5. 10 to the 5th centimeters. So that makes life a lot easier. All right, so it's just the same number, 262.5, but now it's times 10 to the 5th, all right, centimeters. And the volume of any sphere, let me just do that here. The volume is 4 times pi divided by 3 times the radius, which is 262.5 times 10 to the third, but I've got to cube that. All right, so that's pretty much what the problem is about. All right, so here's this one here. Let's clear this. All right, so here we go. All right, so it's going to be 262.5 times 10 to the third. All right, so now I've got to cube that, raised to the third, and then times 4 times pi, and then divided by 3. All right, so this is going to give me the answer in non-scientific notation. All right, so here, let me quickly figure this out. 1, 2, 3, 1, 2, 3. So that's 6. There's 12. There's 15. So 7.58 times. I already forgot what the number was. All right, I realized I did this wrong. So it should be 2. I put the wrong thing in. 262.5. I'm running out of time. I want to make sure I do this right. Times 10 to the 5th. All right, that's what I did wrong. Times 10 to the 5th. Now I raise that to the third power. All right, and then hold on. Raised to the third power times 4 times pi divided by 3. All right, so this should be all right. So that should be the answer. Let's see. So this is going to be. I'm going to store this. And now this is correct. This is times 10 to the 22nd. All right, that's what goes up here, right? So it's going to be 7.58 times 10 to the 22nd centimeters cubed. All right, so that there. So now I've got that in my calculator. All right, so I'm going to store that. And then I'm going to put this number in. So 259 times 10 to the 23rd divided by the memory recall equals. All right. So 2.59 times 10 to the 23rd divided by memory recall. So that's the volume. So you get an answer of 3.41. So we would round it to one place past the decimal. The answer to this density problem would be 3.41. 3.4 grams per centimeter cubed. All right, so which is approximately the density of rock, which is usually around 3 grams per cubic centimeter.